Thank you very much. Good evening, South Cheshire. A pleasure to be back to talk to you once again, extending the talks I gave you last year, which were parts 1 and 2 of the series Exploring the Solar System. It's a trilogy in 6 parts, and this is part 3, and you'll be getting part 4 after the break. So yes, this is Exploring the Solar System, how we go about exploring the solar system with telescopes. For those of you who've forgotten, part 2 was how we explore the solar system with spacecraft, how we actually visit. This is how we get information about the solar system, basically staying on Earth, or at least close to Earth. So I'll be just very briefly talking about the 400 years that we've had telescopes, thinking about the first views of the solar system with very early telescopes, and perhaps looking at some of the more latter views that we get with the more recent telescopes, and asking the question, where next, in terms of where telescopes are going. So I'm fairly sure we all know some of the history of telescopes. It started, we can't claim that Galileo invented the telescope, but he was certainly one of the first people to take the newly invented telescope, point it at the night sky, and he was one of the first to make records of what it was he was seeing. And that's why we remember Galileo in terms of the very early history of the telescope. Of course, the telescope then, a refracting telescope using lenses rather than the more modern mirrors, relatively small, only a few centimeters or so in size, the objective lens. And throughout the next few centuries leading up to the present day, telescopes, of course, have got larger and larger. We want larger apertures, partly to collect more light, and partly because larger apertures, regardless of whether they're lenses or mirrors, larger apertures will give us more detail. So we can see fainter objects and we can see more detail in those objects. So there's always this drive towards larger and larger telescopes. As well as using lenses, it was realized after a little while, lenses often introduce false color because effectively they're acting like little prisms. And so developing telescopes that use mirrors, both Newtonian and Gregorian designs, developed into the large telescopes that we know today, where we've basically put lenses to one side, because getting lenses bigger than about a meter is almost impossible, whereas mirrors that can be supported from the back rather than just around the edge can be arbitrarily large. Not quite, but we'll see some of the larger telescopes shortly. At the end of the last century, around 1918, we had the Hooker telescope, 2.5 meters or 100-inch telescope, the famous telescope that ultimately allowed Hubble to look at galaxies and measure their spectra and determine that the universe is expanding, which of course changed our view of the universe in which we live. And also another great telescope built by George Ellery Hale was the Hale telescope. It wasn't named the Hale telescope, unfortunately, until after his death. In the early 1920s and 30s, this was put together. It was finally commissioned in the 1940s, but unfortunately by then Hale had died. So the Hale telescope was in fact the largest telescope in the world when I was born. And it was the largest telescope in the world for my childhood. And it was the largest telescope in the world for most of my adult life. It was actually took that prime position for the best part of half a century, which is pretty amazing for any scientific instrument. We now have telescopes that are larger, but in terms of their efficacy, in terms of what they can do, we now live in an era of space telescopes, and who isn't familiar with the iconic Hubble Space Telescope? Now, of course, getting rather old, launched in the 1990s, well, basically 1990, serviced in the early 1990s, it's now getting very old, but it's still producing wonderful images. And of course, even more recently, the James Webb Space Telescope launched on Christmas Day 2021. But those are by no means the largest telescopes. Space telescopes are a finite size simply because it's difficult to get large optics into the top of a rocket and send them off to either Earth orbit, or in the case of the James Webb, send it off to park at a Lagrange point out 1 million miles above the midnight point of Earth. But here on the ground, we don't have limitations of size that we do for space telescopes, and so telescopes are getting ever larger, such as the European Extremely Large Telescope, which will be coming online hopefully very soon, only maybe a couple of years away now, the incredible 39-meter diameter mirror there. You can perhaps barely see, but there are a couple of people standing in front of it there. Gives you an idea of scale. We have certainly come an awful long way from the telescopes that are centimeters in size through telescopes that are meters in size in terms of the collecting diameter, and now we're talking about tens of meters. It is still possible to build larger, but of course they start to get very expensive when you get to that sort of size. So let's remind ourselves about what we're talking about, not the development of telescopes per se, but how did telescopes help us get a handle on what's going on in the solar system. One of Galileo's first and rather famous observations is that when you look towards Jupiter, which was of course just a point of light in the sky up to this point, he said, our own eyes show us 4 stars which wander around Jupiter, as does the moon around the Earth. The first evidence that not everything rotates around the Earth. The Earth is not the center of the universe, because at the very minimum, these objects seem to be rotating around Jupiter, not around us. And so he recorded from night to night Jupiter and these stars. If they were background stars, you wouldn't expect them to follow Jupiter as Jupiter moves through the night sky. And he made meticulous observations of where these satellites were day after day after day, hence proving that some satellites moved around Jupiter quite quickly and others moved around more slowly, just like the planets do in the solar system. So he didn't understand the universal law of gravitation, which came somewhat later, but at least we were now clear that not everything rotates around the Earth. And this, of course, helped in our argument that, okay, it looks like the center of the solar system is the sun, which we now know, not the Earth. And when it came to looking at other planets, again, there was some confusion when he looked at Saturn. Remember, we're talking about optics which were nowhere near the quality of optics that any amateur can hope to buy these days. When Galileo looked at Saturn, he got a rather confusing view. 3 round stars, the middle considerably larger than the 2 lateral ones. So he couldn't resolve what was going on Saturn due to aberrations in the telescope, which were inevitable with any hand-ground lens. But this was back in 1610, and in the decades following, lots of people got telescopes and started looking at Jupiter and Saturn and other planets. And the confusion reigned for quite a few decades because nobody was too sure what it was they were looking at. Is Saturn actually 3 objects? Is it an object with handles? Is it an object with ears? What exactly is going on? And although they all seem rather different, it wasn't long before people realized, well, actually, everybody is looking at the same thing, but depending on the quality of the telescope, you get aberrations which make you think you might be looking at one of these shapes. And a few decades after Galileo, a number of people, including Huygens, here credited in 1659, basically said, I think what everybody is looking at is a globe, but it's a globe with a ring around it. We don't know what that ring is made of, but it looks like we're looking at a sphere surrounded by a ring. And of course, that is extremely close to what we now know Saturn to be. It's actually a very thin ring. It wasn't appreciated just how thin it was. They thought maybe it was thick. If we can see it, it must be thick. But it actually turns out to be a large number of tiny particles all orbiting, and the ring thickness is tiny compared to its diameter of some 250,000 kilometers or so. So eventually, some of the confusion over Saturn was tidied up. But there was plenty of confusion over other planets. Early telescopes weren't very good at looking at the tiny disks, for instance, of Mars, and it needed a little bit of time for telescopes to improve to the point where people could start making observations of detail on the surface of Mars. So, for instance, Schiaparelli was making detailed notes of Mars. This is his notebook, dated 1890. I love the fact that his notebook has got a few sheets of paper that have been pasted in with half stamps. He didn't want to waste a full stamp, so he cuts the stamp in half and then pastes this little half page in there, presumably to cover something which perhaps he changed his mind. But he's got drawings here of various features which are blown up on the other side of his notebook, and he was seeing night after night after night, he was seeing linear features, originally called canali, indicating channels, but unfortunately that was mistranslated when it came over from the Latin, from the Italian into the English, and a lot of people assumed that what he was talking about were canals. And channels or canals might sound very similar, but one set are natural and the other set are effectively artificial. And therefore people picked up on the idea, well, if you are looking at canals, presumably this is irrigation, presumably this is water being brought down from the north or south poles to irrigate the equatorial regions. And some people said, yes, I can see these canals as well. And one great proponent was in America, Percival Lowell, in the late 1890s and early 1900s. He picked up this idea and said, yep, I can definitely see all these canals. And this is proof positive that we have basically life on the planet Mars. There can be no doubt living beings inhabit our neighbor world. Professor Percival Lowell, it says here, recognized as the greatest authority on the subject. I don't know who recognized him. Maybe he recognized himself as the greatest authority on the subject, but he was convinced that A, these lines were there, B, these lines were definitely canals, not channels, and that was proof positive that we have Martian neighbors. And you're all familiar with the hubbub of War of the Worlds, the book, the radio program, the film, etc., and the idea of Martians looking down on the Earth. Lowell actually used this telescope, a rather large refractor, many centimeters in diameter in the object lens, and of course funneling all that light down to a relatively small eyepiece at the business end. There's Lowell sitting at the eyepiece end of the telescope. And it's thought that what was probably happening was that an awful light was being gathered by this large objective lens. There was a tiny exit pupil on the eyepiece. What happens when you go to the optician and they shine a light in your eye, a very narrow beam of light in the back of your eye? You see the blood vessels on the back of your eye. And perhaps that's what was happening. When straining to see detail on the surface of Mars at high magnification, maybe what was happening was light was being projected onto the retina of the observer, and they were mistaking seeing occasional flashes of that looks like a straight line, oh, it's gone. That looks like a straight line, oh, it's gone. These were simply ghosts, if you like, of the blood vessel pattern on the back of the eye. So a lot of people said they thought they could see the same thing, whether that was simply going along with, well, if I don't say that I can see these canals, no one's going to think I'm a good observer, so I better say I can see them as well. But eventually, the idea of Schiaparelli's, I can definitely see canals, there were definitely straight lines. Sooner or later, people looking at Mars said, well, yeah, oh, no, not really, no. I can see edges, I can see light and dark, and I can see edges, but I can't see any of these straight lines that you claim are crisscrossing the surface of Mars. So from the 1900s, the idea of a red planet crisscrossed by canals eventually gave way to the sort of planet we know and love now. This is a much more recent image, of course, from Hubble in this case. And so we're seeing rather dark, rocky areas. This is basalt produced by the volcanism of Mars, and a whole load of rather lighter colored sand, effectively oxidized, rusty, if you like, sand getting blown around. And so these markings do change as the sand and the dust gets blown over the darker rock, but at no point do you actually see very obvious linear features. You might get the hint of them from time to time, but no, there are no canals on Mars. When we think about what amateurs do with telescopes, again, the telescopes that we have access to now, much larger than the optics from Galileo's day, and indeed much higher optical quality, because effectively they are diffraction limited, not aberration limited. In other words, they're only limited by the laws of physics that say this is the amount of detail you can resolve in a lens of a given size, or a mirror of a given size. Whereas in the early days, they were limited by the aberration, the fact that they couldn't make lenses perfectly to focus light. These days, we have all sorts that we can choose from. We can go for dioptric telescopes, i.e. those that use lenses. On the right, we can go for catoptric telescopes, i.e. those that use mirrors. Most of us, of course, don't bother with those labels. We just call them refractors and reflectors. But the name sometimes lasts when we look at those telescopes that have an element of glass and mirror. That's why they're still sometimes called catadioptric telescopes, or CATs. The Schmidt-Cassegrain design or the Maksutov-Cassegrain type design. Of course, for the same reason that professionals always want larger and larger telescopes, the double whammy, larger apertures mean you can see fainter objects because you collect more light, and you have higher resolution so you can see more detail in any of those objects. So amateurs also want to go, generally speaking, from the smaller telescopes to the larger telescopes if their pockets are deep enough. And if your pockets are really deep, you can lust after a telescope like that. And if you're not too sure of the scale of this thing, that gives you an idea. Yes, they are rather massive and rather large. This one is about 300 kilograms or so. Don't worry about it being really massive, because Meade is no more, but the Meade telescope we're seeing pictured there, Meade understand that you don't want anything that's too massive, so they make sure that your bank balance will be a lot lighter once you've actually bought this thing. But if we look at what the professionals are doing in terms of pushing towards ever larger mirrors, this is a graphic showing you the relative size of mirrors or lenses, not going all the way back to Galileo. The smallest one you can see here is effectively the largest refractor, the 1 meter diameter lens of the Yerkes refractor. So you can see that mirrors have got a lot bigger since the turn of the last century. The largest telescope in the world at the moment is the Gran Telescopio Canarias on the La Palma island of the Canary Islands. That's been the world's largest for quite a few years now, is going to be overtaken within the next few years, but at the moment it is still the world leader. If you compare that with space telescopes down in the bottom left-hand side, perhaps not surprisingly, space telescopes much smaller because it's difficult to get them into space in the first place. Recently retired Gaia finished its mission last year after spending 10 years taking trillions of measurements of star positions, so that we now have the Gaia catalogues of where the stars are, how they are moving, and hence we now understand the dynamics of the Milky Way much better than we did. The large James Webb, you can see much larger than the Hubble Space Telescope there, and also small Kepler. So that's not every space telescope, that's just a representative collection. And it reminds us that space telescopes are tiny compared to some of the larger mirrors that are coming online. We don't make large mirrors in one piece anymore. We make them out of segments because it's a lot easier to make a large number of small segments and then put them all together to get the large surface that we need. So hopefully before too long, the European Extremely Large Telescope, the ELT, will be coming online. Nominally 39 meters in diameter. This particular graphic indicates that it should be online in 2028. So let's hope that's still accurate. Maybe it's only a couple of years before this particular telescope is operational. And you can see it's so huge, the Cassegrain hole in the middle there is larger than some of the telescopes of not that many years ago. The Hale telescope, as I said, that was made in the 1940s, an amazing piece of engineering, and it remained essentially the largest telescope in the world until the Keck came along, the Keck on Hawaii, a mere 5 meters, but bear in mind the largest telescope in the world at the moment is only 10 meters. The largest telescope in the world is only twice the diameter of this one, and this was built in the 1940s. So you can see that, yes, telescopes are getting larger, but it's quite amazing how one particular telescope stood the test of time and is still operating and is still scientifically a very valuable instrument. Where are these big telescopes sited? Well, in principle anywhere, but there are certain places in the world which are considered to be the prime places to put telescopes, the places with the best seeing conditions. Volcanic islands tend to be very good. Volcanic islands surrounded by sea, you get very stable air, and therefore if you stick them on the top of a volcano, you get very stable winds and very stable air movements. So putting telescopes on the Hawaiian Islands is a very good idea. The largest telescope, as I said earlier, is on the Canary Islands, a similar little archipelago of volcanic islands out there in the Atlantic. And the third place to put a telescope, which has become popular in the last decade or two, is the high deserts of the Atacama in Chile. Not a volcanic, but because it's part of the Andes, again, the way the wind, the way the air moves across the Pacific and goes over the Andes gives you very stable conditions. If we have a closer look at that particular point in the Andes there, this is Charapaxón. You can see an observatory there on a mountain top, as photographed by a neighboring mountaintop, where I think there's another observatory. This particular one, I think photographed from, I think this was Gemini South. So you can see it looks a little bit hazy in the background, but bear in mind, most of the haze you can see is below the level of the observatory. The observatory is high enough that you are above a lot of the atmosphere. If you're at a height of order 10,000 meters or so, you're not at the top of the atmosphere, but you're above a fairly large fraction of the atmosphere, which is why it's difficult to breathe up there, and astronomers have to acclimatize if they ever go up to these high altitude observatories. Of course, you're not limited to something like 10,000 meters. If you want to observe, you can go higher, but there are no mountains higher than that sort of level. But you can put your telescope in the back of a 747 if you want to. So the Stratospheric Observatory for Infrared Astronomy, or SOFIA, they did precisely that. They put an infrared telescope in the back end of the 747, made sure it was totally stabilized so that even if the 747 moved around, the telescope stayed absolutely steady. And they flew this at relatively high altitudes to make sure, again, they were above most of the absorbing effects of the infrared, which is a problem if you ever want to put infrared telescopes on ground level. A lot of the atmosphere does absorb the infrared compared to the visible. Now that we have the James Webb Space Telescope, you could argue that we don't need SOFIA anymore. So SOFIA was retired a little while ago, about a year or so ago. So if any of you fancy a second-hand 747, keep an eye open on eBay because it should be coming up any day now. And we're all familiar with the idea of the Hubble Space Telescope from 1990, now 35, 36 years old. It hasn't failed yet. Sooner or later, its gyros will fail, and then it won't be able to take any more images. As soon as it's not able to point accurately at a patch of sky, if its gyros fail to the point where it keeps wandering, it won't be able to take any nice images, even though the optics are still good. If it can't point accurately, it won't be able to continue. So in the next few years, it is going to fail. And we're all, again, familiar with the James Webb Space Telescope, launched in Christmas Day 2021, basically tested almost to death in the laboratory. And then when they were happy that everything was okay, folded up like a piece of origami, put onto the top of a rocket, and then fired off into the parking spot that is 1 million miles above the midnight point of Earth, the so-called Lagrange point 2, L2, where other satellites have been working. Gaia used to be at L2, and now Gaia has been pushed away from L2 to make more space for other space telescopes, which ultimately are going to occupy the same point in space. Let's have a very quick look at what we can learn, for instance, by comparing the Hubble Space Telescope with the James Webb Space Telescopes, the two biggest space telescopes that we have operational at the moment. If we look at Jupiter in the visible, we get a view that's sharper, but essentially very similar to what we see in amateur telescopes. We see a sort of a salmon-y, slightly orangey, slightly reddy set of bands. And we think that's due to the composition of these belts, the fact that there's almost certainly sulfur and phosphorus and other compounds in there which are giving it the characteristic colors. If we look in the infrared, James Webb might see similar structures in that we can see the storm systems and we can see the great red spot, though it doesn't look red in the infrared. We see similar structures, and again, by thinking about what particular depth we're actually observing at different infrared wavelengths, we can get an idea of, are we looking at the winds traveling at different heights in the Jupiter atmosphere? We also notice there appears to be color fringing at the top and the bottom. Surely that can't be aberration of the James Webb. Surely it's optically better than that. Well, yes, this color fringing is nothing to do with the optics. That's simply the fact that we've got aurora borealis and aurora australis. In other words, we've got northern lights and southern lights. Jupiter has a very strong magnetic field. Again, radiation from the sun, energetic particles, protons, electrons are caught in Jupiter's magnetic field and give aurora, much as they do here on Earth. If we have a look at the Hubble Space Telescope view of Saturn, I guess none of us would be surprised that again it's sharper, but essentially very similar to what we see through amateur telescopes. When we look with the James Webb in infrared, it is somewhat surprising what we actually see. depending on which wavelength you use to make the observation. Here, James Webb has observed at a particular wavelength where the planet itself tends to absorb most of this particular wavelength because there's a lot of methane in the atmosphere. They've chosen a wavelength that absorbs that, and so the planet's globe, the actual planet itself, looks relatively dark, but the rings look amazingly bright by comparison. That's simply because the rings themselves are made out of huge numbers of tiny icy particles, and each of them is very effective at reflecting infrared light from the sun. So the planet tends to absorb, the icy particles of the ring system tend to reflect, and so you get this rather odd situation that the rings become much brighter than you might expect. And they've used that to advantage, for instance, to look at Uranus. Same idea. The planet itself tends to absorb quite a lot of infrared radiation, but the ring system, which is very faint and difficult to see in the visible part of the spectrum, when you look at how effectively it reflects infrared light, because each of these are tiny icy particles, they tend to reflect very effectively. And so if you can make the disk of the planet a little bit darker, then the rings stand out even more prominently. Looks like we have a storm system raging, a very bright spot. As well as the pole itself being brighter, there seems to be a storm system raging. When Voyager went past Uranus back in the 1980s, it was thought not much was going on. It looked, dare I say it, a little bit boring. Not much seemed to be happening. Compared to the spectacle of looking at Jupiter and Saturn, it seemed like with Uranus, there wasn't much going on. But bear in mind, it only spent hours going past the planet. Remember, Voyagers were on their way from Jupiter to Saturn to Uranus to Neptune, and therefore they didn't hang around and spend months imaging the planet. They only had a few hours as they were flying by because they had a gravity assist to Neptune. Yes, question?
I'm just wondering, it's supposed to be on its side, isn't it?
The axis of rotation, yes, is tilted.
What would cause that? Because most of it's gas. Certainly, if anything impacted, it wouldn't make any difference.
Oh, it would definitely make a difference. Just because it's gas doesn't mean it won't be affected by an impact. So one assumes it was probably an impact a long time ago that caused its axis to change. If you get one mass interacting with another mass, you can change the angular momentum, regardless of whether you're talking about rock or gas. It doesn't matter, it's still matter. And therefore, you can get the impact of a body affecting the spin axis, even if that spin axis is the spin of an ice giant. And strictly speaking, it's not necessarily all gas, much like Saturn, Jupiter, and the ice giants. Just because the outer part is gaseous doesn't mean it hasn't got some. For instance, we still don't know whether Jupiter has got a metallic core or not. It might be solid hydrogen in the core. And so there will be an interaction between the core and the outer parts. So yes, Uranus is spinning at a very jaunty angle, which is one of the reasons we see these rings like that. Rather than like Saturn, we see them almost edge on. With Uranus, depending on the time of year, we can see them almost face on. So when Voyager went past Uranus, it didn't see much, but now we're on Earth and looking at the planet, we can see detail. And of course, that's one advantage of telescopes compared to spacecraft, is we can turn the telescope on the planet essentially anytime we like. With a spacecraft, it's done its job. It's flown past and it's now doing something else. We have effectively one shot with a spacecraft. But here, we can choose to look at a planet once a day, once a week, once a month. We can choose to make a whole series of observations that we can't with a spacecraft. And a similar sort of pattern when we look at Neptune. Again, we see Neptune with its rings. Neptune's rings very faint in the visible, but they show up quite nicely in the infrared. And again, for a similar reason, it looks like we've either got a very bright star in the background. In fact, that's one of the fainter moons of Neptune. But that moon looks exceedingly bright, even compared to the parent planet, simply because of the nature of what's on that moon. Triton has got a surface effectively of solid nitrogen, so it's effectively a mirror almost as far as infrared is concerned, and so the infrared light, some of which is absorbed by Neptune, is reflected very efficiently by the surface of Triton. So Triton comes out very bright compared to its parent planet. Let me just finish with what's coming next. I've said something about what telescopes have done for us in the past. Recently operational is the LSST, which used to be called the Large Synoptic Survey Telescope. That's where the acronym comes from. They've renamed it the Chamonix Telescope. So this Chamonix telescope, which is sitting in the Rubin Observatory in Chile, has been operational now for, I think, a few months or so, and it's going to be surveying the sky. 8-meter diameter mirror with a huge camera. You can get an idea of the scale of the camera from this token person standing next to it. And the LSST acronym has now been reused and borrowed from the Large Synoptic Survey Telescope, and it's now been reused as the Legacy Survey of Space and Time. That means lsst.org as a domain doesn't need to be thrown away. You just repurpose it and define the project as LSST. It's going to be a survey that will run for about 10 years or so, nominally from now until 2035, and it will be surveying the sky with its huge gigapixel camera. It'll be mapping out the sky that it can see, roughly speaking, once every 3 nights or so, and therefore it'll be repeating its observations of chunks of sky night after night after night for hopefully the next 10 years. And ultimately, as a survey telescope, it'll tell us what's up there. Rather than getting big telescopes to point at particular objects, the LSST will survey and tell us what is up there. Once it finds interesting things, it'll then tell big telescopes like the European Extremely Large Telescope, go point at this object because this looks really interesting. With the larger mirror, you can look at really faint objects and collect a lot of light and get good resolution. Again, I remind you that there's a couple of people standing at the bottom there, and there's also a couple of people standing there at the Naismith focus of the telescope. Hopefully operational in 2028. Construction is well underway. I think it's on schedule, so watch this space. If I piqued your interest, you can go and find from these various web pages what's happening with telescopes that have been around for years, and also what's happened with telescopes that have just come into commission, and telescopes that will be arriving shortly to tell us more about not only the universe, but in particular what's happening in the solar system. Thank you very much.